stage, we're only going to be talking about circuits composed of 1 and 2 qubit gates. And the depth of such a circuit, is the number of layers of gates, where within a layer the gates need to not overlap in terms of the number of gates they act upon. And we're going to be interested in constant depth circuits. Okay, so what are these constant depth or shallow circuits good for? Well, we've known since 2002 that, and you know, much follow-up work in this sort of line of quantum computational supremacy, that shallow depth quantum circuits can sample from probability distributions that if you could sample from them using an efficient classical computation, it would collapse the polynomial hierarchy. And you know, recent work has tried to make this robust against error. We also know that shallow quantum circuits can solve certain linear algebra problems faster than classical algorithms. And I believe that Robin will speak a bit about this on Friday. I guess one comment is that this, in a sense, can be viewed as, so when I say faster, I mean faster in terms of circuit depth. And this can be viewed as some kind of local quantum algorithm that beats local classical algorithms. And so part of the motivation for this work is just to understand whether or not these shallow quantum circuits can be used for other purposes, and whether or not we can prove or establish you know, limitations of shallow quantum circuits in these scenarios. So in particular, again, another topic that has been mentioned a few times already has been these variational quantum algorithms, which are sort of attractive for near-term implementations because they're very sort of amenable to be implemented on devices with, you know, taking all sorts of different shapes and forms. So the sort of main goal here is to compute the ground energy of some Hamiltonian. Here I'm going to assume that it's a sum of local terms pi. When I say, sorry, I misspoke. These are not assumed to be local. What I'm going to assume here is that these pi's are tensor product operators. They're a tensor product of single qubit operators. And we're interested in the minimum energy, and the goal is to compute that using a quantum computation. And so like the only assumption that you need to use these variational quantum algorithms is that your quantum device prepares some subset S of n qubit states and can measure the energy of some given state psi in that set. And then of course you're going to try to use the quantum device to minimize the energy over states in the set S, and you will hope that that approximates the true minimum energy. So I think we've seen this sort of diagram before. You know, these variational quantum algorithms, you start with some knob settings that determine some state psi that your device can prepare. You compute the energy, and typically this is done by focusing first on a single term. So maybe this is some Pauli operator, and you measure all the qubits in that basis consistent with that Pauli operator and compute the expected value of that Pauli by repeating this several times. And then you can sum up, you know, the answers that you get for the different Pauli terms to compute an estimate of the energy. And then, of course, so if you want to compute the minimum energy over states in S or approximate it, the strategy that has been suggested is you start with some initial knob settings, you compute the energy, and then use a classical computer to sort of go downhill. And you know, this has been suggested and implemented in various ways. And you know, these algorithms don't have performance guarantees, although I know that, you know, I should say that not all variational algorithms have performance guarantees. Certainly the ones that Eddie was speaking about, I mean, he has established certain performance guarantees. But you know, one thing we were interested in is, do these algorithms have an advantage over classical algorithms? And you know, if we can't show in some kind of general setting that they have an advantage, or we can't establish that, then another way to look at that question is to ask whether or not we can classically simulate them. And so that was the kind of approach that we took. And you know, one thing to observe is that the quantum computer here is used only to approximate expected values at the output of these shallow quantum circuits. And so we ask, what is the complexity of that task? So in particular, we have a shallow quantum circuit U. We have a tensor product observable O, so it's like O1 tensor O2 up to On. And we want to know how hard is it to approximate this mean value on a classical computer so that you don't need to run it on a quantum computer. Other questions about that? Okay. Okay, so this is the same as what I just said. I wrote out the tensor product here of the operator O. I am going to assume that all the terms in the tensor product have spectral norm at most 1. And there's sort of an interesting special case. I mean, so if I asked you what is the complexity of computing this quantity, maybe you would first think about this case. So let's take O to be a projector onto a computational basis state. Well, then this mean value is just the output probability, so the probability of obtaining the bit string x after applying the circuit to the all zero state. And we know that computing output probabilities of shallow quantum circuits, at least computing very precise estimates, is a very hard problem. So that gives you a little bit of insight, and I'm going to discuss this more in the next couple of slides. So there's two versions of the mean value problem. The one I just sort of spoke about, computing a very precise estimate, we'll talk about in a moment. But the first version is what I'll call the additive error mean value problem, where we're given an inverse polynomial precision, and we want to compute an estimate that just achieves that additive error. So the difference between the estimate and the true value in absolute value is at most this inverse polynomial quantity. And you know, this you could actually do on a quantum computer, right? I mean, you run the circuit, you compute you measure the observable, and then you repeat and accumulate statistics until you get the error below epsilon. Okay. On the other hand, this more precise type of estimate where we ask for a relative error, so mu tilde minus mu is now, that difference is proportional to mu. So if the mean value itself is very small, you know, this is asking for a much higher precision in the estimate. And this problem is sharp p hard, and so you would not expect to be able to solve it even on a quantum computer. Okay, so so I would like to understand, you know, the complexity of this problem for constant depth circuits, tensor product observables, and you know what we did is we studied this for three sort of special cases. We were not really able to completely characterize the complexity of this problem for constant depth circuits, but we have sort of three interesting special cases where this problem becomes easy for classical computers, and so that's what I'll tell you about in the rest of the talk. So just for comparison, if U was a polynomial-sized circuit, the observable is just projected onto a computational basis state, then this precise version, as I mentioned, is sharp p hard, and the additive error version, I already said it was can be done efficiently by a quantum computer, but in fact it's BQP complete. So we want to understand now the case where the circuit is not just a general polynomial-sized quantum circuit, but instead is a constant depth circuit. Okay. So the first case is a case where the single qubit observables in the tensor product are each individually close to the identity. So here we have an observable, and each of the OJs, those are single qubit observables. Now they're very, very close to the identity, but in a way that only depends on the depth of the circuit and not on n. Okay? So this tensor product need not be close to the identity. Okay? Just the individual terms. And in this part, we're going to consider this much harder type of estimate, this relative error estimate, which in the general case, even for constant depth circuits, is sharp p hard. So you might ask, well, when would you ever encounter this sort of observable, right, where all the terms in the tensor product are very close to the identity? So one place you might encounter it is if you had a noisy implementation of a shallow quantum circuit, and you apply your this should be inside the bracket. You apply your shallow quantum circuit to the all zero state, then you apply a noise map where you just flip each bit with some probability p, and then you measure the output probability of getting 0. Okay? So this noisy mean value, mu prime, it's straightforward to show that it can be written as 1 over 2 to the n times noise-free mean value with different single qubit observables that now depend on the noise rate p. And so this type of noisy mean value, you know, can be expressed in the form that we need for in the form that I mentioned in the previous slide. So that, in other words, these observables are very close to the identity in the very high noise regime. So when the noise rate is very close to 1/2, in a way that only depends, again, on the circuit depth. Okay. So what do we prove in this case, where the single qubit observables are close to the identity? We show that there is a deterministic classical algorithm which outputs an estimate mu tilde such that the log of mu tilde is close to the log of mu. And this, if we exponentiate this equation, we get, so this is an additive error in the log, which translates to a relative error in the estimate itself. And the running time of the algorithm for fixed depth d is polynomial in n in the inverse error. So this solves this relative error mean value problem for this restricted set of observables. And the runtime can be improved for geometrically local circuits, for example, in 2 dimensions. And the algorithm is based on a polynomial interpolation method, which is due to Barvanok, and which I'll just describe briefly over the next couple of slides. So we consider a polynomial where, previously we had considered O1 tensor O2 up to On, but now we're going to define an observable Oj of epsilon that interpolates between the identity, this should be O sub j. And so now this expected value of O of epsilon, which is the tensor product of all of these interpolated observables, that quantity is now a degree n polynomial in epsilon. And when we take epsilon to be 0, all of the single qubit observables are the identity. And so this expected value, the polynomial takes the value 1 when epsilon is 0. And when epsilon is 1, then all the single qubit observables are the things that we want. And so then that's the mean value that we want to compute. It's also true that the derivatives with sort of low order can be computed efficiently. And so one way to see that is just that, like for example, if we take the first derivative of this polynomial, then what happens is, we pick up, well, it can be expressed in this way as a sum over j from 1 to n, and we have u conjugating the observable Oj minus the identity. And because u is a depth d circuit, the support of this operator is upper bounded by 2 to the d. So this quantity can be computed using a computation on just 2 to the d qubits, which is constant for constant depth. And likewise, if we have like higher order derivatives, for example, k growing logarithmically with n, then we can compute those derivatives efficiently. So we have a polynomial, we know its value at 0, we want to compute its value at 1, and we can compute the low order derivatives. So the natural thing to do is to try to use some kind of Taylor series expansion. But to use Barvanok, Barvanok's suggestion is a little bit slightly better than this, because if we use a Taylor series approximation, we'll get some kind of additive error. And what Barvanok says is that we should use the Taylor series for the log of the function itself, the log of the function rather than the function itself, because an additive error in the log translates to a relative error in the function. Okay, so he says approximate the log by its truncated Taylor series, so that's the natural thing to do. So we truncate to order p. So here now we're writing g for the log of the polynomial. And what Barvanok's theorem says is that you can use this method and you get a very good approximation to the log of the polynomial, even with a small value of p, like p growing logarithmically with n. But that, in order to use this, you need the polynomial to be zero-free on a disk that contains the region where you want to interpolate to. Okay, so there's, to use this method, you need to be able to compute these derivatives of the log of the function, and you need to establish a zero-free region for the polynomial. And then you get this low degree, this good approximation. Okay, so that's what I just said. We need to compute derivatives. We know how to compute the derivatives of f, and that translates, it's very straightforward to go from those to the derivatives of g. And so the hard work that we do here is showing that this polynomial is zero-free as long as the condition on the observables is met. And I'm not really going to describe that here. This is the theorem that we prove. The main technical tool here is the Lovász-Lóka lemma, which somehow, we define a probability distribution which is proportional to the function. And then, yeah, I have some more slides about this, and if there's time, I can get to them, or you can ask me about it later. But we have this result which says that these polynomials that come from shallow quantum circuits have a zero-free region that the radius decreases exponentially in the depth, but does not decrease with n. Okay, and you could ask, can this bound on the zero-free radius can be improved? So you could go to, higher noise rates or lower noise rates, and you can interpolate further. And in fact, you can show from a simple example that there exists shallow quantum circuits and sets of observables that in the worst case show that this bound is very close to optimal. So in other words, there's one of these polynomials which has a root that indeed is inverse exponential in the depth of the circuit. However, it's also interesting to note, and we show that for random circuits, the zero-free radius is typically much larger, and in fact, asymptotes to 1 as n goes to infinity. So that's a major difference between random circuits and random shallow these are not shallow circuits here. These random circuits have to be drawn from an ensemble that forms a 2 design. But if you have that, then this zero-free radius is much larger. And we're not sure what you can do with this observation, but it is kind of curious. Okay, so that's the first case. So when we have constant depth circuits, observables that are individually close to the identity, then in fact this relative error mean value problem can be solved in P, and of course then the additive error one can too. The next case is a slightly more general setting. So in here we want to consider, U is again a shallow quantum circuit. O is now just any, for the purposes of this slide, O is just any tensor product observable where these are Hermitian operators. Okay? And what this theorem says is that we have a classical algorithm which estimates the absolute value of the mean value to within an additive error delta and has a sub-exponential scaling with n. Okay, so this algorithm, unfortunately, it doesn't do exactly what we want because it estimates the absolute value of the mean rather than the mean itself. So for example, if you wanted to take a shallow quantum circuit and estimate the expected value of like Pauli Z tensor n, you could estimate its absolute value, but you would not get the sign information using this algorithm, which has a sub-exponential scaling in n. But this does sort of solve this additive error mean value problem if the observables are positive semi-definite, in which case the absolute value is just equal to the value of the mean itself. And removing this condition that this fact that we have to take an absolute value here is kind of mysterious, and I don't know how to get rid of it. Okay, so how does this work? So again, we use some kind of polynomial method, but it's a very different polynomial method. So first, if you just imagine, so I'm going to give you a proof sketch, but I want you to just imagine for a moment that O is unitary, okay? In fact, it's very easy to reduce to that case. So if O is unitary, then this whole U dagger OU is itself a shallow quantum circuit. And so we could, instead of estimating this, we could estimate its square. And the square of that is just, of this form where U here now is U dagger OU from before. Okay, so now we want to estimate like the output probability of getting 0 after applying a shallow quantum circuit to the all zero state. And to do that, you can use a method which has previously been used by Harrow and Eldar, and also has come up in other places, where we define a local Hamiltonian, which is the sum of the projectors onto the one of qubit j conjugated by the unitary U. This Hamiltonian has the property that the state that we care about, that we want to, this is the output of the shallow circuit, is the unique zero energy ground state of this Hamiltonian. And then our goal is going to be to construct a low order polynomial function of this Hamiltonian that approximates the projector onto this state. And this can be done using polynomials that come from query complexity. In fact, you could use just a shifted and rescaled Chebyshev polynomial, but this polynomial from query complexity does a little bit better in the dependence on the error. Okay, so we get this polynomial function of this Hamiltonian, which is sort of low degree, like low meaning sublinear in n. And then the desired approximation is just to take the expected value of that polynomial function of the Hamiltonian sandwiched between all zeros. And an exact computation of this quantity can be done in subexponential runtime using the fact that the polynomial degree is subexponential in n. Okay, so that's kind of the sketch of that algorithm. And so for the case of constant depth circuits where the observables are positive semi-definite, well, again, I didn't say this, but the relative error problem is again sharply hard. But the additive error problem we show is solvable in subexponential classical time. We would really like to replace this with Hermitian and not have the positive semi-definite restriction. But as I said, I don't know how to do that. Okay, so the last thing, and if you... So now, this case may be the most practically interesting. So what I'm going to say here does not rely on anything I said before, and may be of interest to people that are interested in two-dimensional geometries. So now if we have a qubits located at the vertices of a two-dimensional grid, and again we consider a shallow quantum circuit where the gates act between nearest neighbors on the grid, then what we can show is that there's a randomized classical algorithm which solves the additive error mean value problem. So it outputs an estimate to within some given additive error. And the runtime of the algorithm is linear in n for constant depth, but it has a very bad prefactor of 2 to the O of d squared. Okay, so if you could improve this prefactor, this algorithm could really be practical. I mean, as I said, for constant depth, it is a linear time algorithm, but if the depth here is, for example, 7 or 8, you're sort of in big trouble because of this prefactor. Okay. Right, so linear time. So well, it is. So the algorithm is based on a matrix product state representation and a Monte Carlo method. I'm going to sketch it in the last couple of minutes, and then we can go to the break. Okay, so here is the expected value. U is this 2D geometrically local circuit. These are the general Hermitian observables. And so now we're just going to redefine, we want to just write this as an amplitude of a quantum circuit. So we're just going to redefine, we're going to define, Q sub j to be the U dagger OJU. So this is now a gate. I'm viewing this as a gate. And the QJs all commute with one another. Okay? And moreover, because U is a 2D geometrically local circuit, it expands the support of the single qubit operator OJ only in its sort of light cone. So you can trace it back through the circuit. You can sort of apply this one layer of gates at a time, and you will see that the support of this Q sub j operator is only in a 2D by 2D square region centered at qubit j. Okay? So now we have a quantum circuit composed of these gates that are only supported on these 2D by 2D regions. And what we're going to do as a first step is we're going to coarse grain the qubits into these supersites of size 2D by 2D. And the reason for doing that is so that each one of these gates only acts between a plaquette of 4 of the supersites. Okay, so this gate now that I've coarse grained my qubits into these supersites, it only acts on these 4 of them. And the ones that are out here that I didn't picture, it just doesn't touch. Okay, so here's my 2D lattice, and here I've coarse grained into these supersites. And this is the amplitude that I wish to compute, and each of these gates commutes with the other ones and acts only on a plaquette. And now what am I going to do? I would like to re-express this as an inner product between 2 states, phi even and phi odd. So phi odd is, the 0 state with all of the gates on the plaquettes that I've shown here. So they're the gates that act on between the odd columns. So here, column 1 and column 3. Phi even consists of all the gates that act on the even columns. So here, just column 2. And the reason that I can separate out the even from the odd columns is because all of the gates commute with one another. Okay? So now I have an inner product between these 2 states corresponding to, this phi odd you can see is actually a tensor product of a state that lives on these 2 columns of supersites and these 2 columns of supersites. And in fact, the state here, which is tensor product with state here, both of those are matrix product states, just because it has this 1D geometry. Likewise, phi even is a tensor product of matrix product states with a different ordering. So for a matrix product state, you have to choose an ordering of the qubits. And here we're choosing a different ordering. And so now we use the fact that the inner product between matrix product states can be estimated using a Monte Carlo method. And actually, this Monte Carlo method is more general. It says that if you have two states and you want to compute their inner product up to a given additive error, then you can always do that as long as the states have the following property. You need to be able to efficiently sample from the output. If you were to measure the state, then you should be able to classically sample from that distribution. And you should be able to, given x, compute the amplitude on x. And so here, because each of these are tensor products of matrix product states, and because matrix product states have that feature, we can just use this general fact that inner products can be estimated for pairs of states that have that feature. Okay. So this is the last thing I wanted to say, which is that when you have a 2D constant depth circuit and Hermitian tensor product observables, then we know how to estimate mean values in BPP. And so, you could say, well, does this have any bearing on the performance of variational quantum algorithms with two-dimensional circuits? And I would say that, maybe yes and maybe no. And the reason maybe no is because the scaling with the depth is very poor. And so I think that, it's still possible that you could significantly beat what can be done on a classical computer, even at low depth, because of this 2 to the O of d squared prefactor. Okay, so what are some open problems? Maybe you noticed that we didn't really solve the big question, which is, what is the complexity of this additive error mean value problem for constant depth circuits? So if you have a shallow quantum circuit and you want to compute the expected value, say, of just z tensor n at the output, how hard is that problem? And we still don't know the answer. And there's some other questions that I'll leave you with. Thanks. Thanks, David. Questions? Yes.
So in the last algorithm for 2 dimensions, this step where you sample from the output of the meters proxies, this is to sample from the output of meters.
Oh, like to within some given error in the total variation distance? No. No, it's just, it lets you, that algorithm will let you compute, as I said, an inner product to some additive error where both of the states in the inner product can sort of be classically simulated in that sense.
And the
but
samples, how those samples are...
Those are just samples. So it's like you have a, this represents an amplitude of a quantum circuit, and you're taking some of the gates and shoving them into this state, and the other ones and shoving them into this state. But if you wanted to sample from the full thing, then we don't know how to do it. Yeah.
So there was a recent paper by Harrow and others that also used Variational's method.
Yes, and Saeed Mehraban, who I think is here. Yeah. Mm-hmm.
So is there a relation to the way you use Variational's method?
Well, I think it's just a sort of versatile technique, and I don't know that there's a formal relationship between the two. No, I think it's just two uses of the same method. Yeah. I don't know. Yes.
Can I see the table again?
Table, yes.
So, what's the difference between second row and the third row?
Second row and the third row? Well, here these observables have to be close to the identity, but these ones are just general positive semi-definite observables.
Oh, I see.
So I don't fully understand what's the difference between a Hermitian operator and the positive semi-definite in the additive error case, because you can always just decompose it to like the...
But this is the individual operators in the tensor product. So a tensor product of Hermitian operators, if you shift by a constant times the identity, is no longer a tensor product of, it's not a tensor product of positive semi-definite operators.
And the problem is that it's not bounded by one, or what's the problem there?
No. So if I understand correctly, I think what you're suggesting is you'd say, well, if you take a Hermitian operator, you can just shift it by a constant times the identity and make it a positive semi-definite operator. But this algorithm requires that the operator be a tensor product, like O1, tensor O2 up to On. So if I take, like for example, Z tensor n, that's Hermitian. So now let's say I shift it, so I take identity plus Z tensor n. That's now positive semi-definite, but it's not a tensor product.
Okay, so let's thank David again.